Hey guys, how's everything going? This is JSer, who is now good at algorithms. In this video, I'm going to continue on brief recaps on top Facebook questions. So let's start. The first one is diameter of a binary tree. So for the diameter is the binary tree is the length of the longest path. Well, it's a recursion. Let's see if suppose there is a longest path. The relationship between the paths for the root to the root is there was only two possibilities. One, this path is in the longest path, or it is not in the path, right? So during recursion, we return two values. One is the diameter of the subtree. The other one is the height, right? The longest path. So for a root, for a node, it should be okay. So if it is not in the path, which means left or right, which this is right, left or right is used, right? So this is the result of the diameter. But if it is if it is collected, then we should be maximum, right? Maximum depth +1 plus itself. Yeah, so it's done. This is easy. Next one, valid palindrome 2. Well, we are given a non-empty string. I may delete at most one character. Judge whether you can make it a palindrome. Well, it's just a recursion. Yeah, check start and don't forget to keep track of the max removals, right? So if mat's the end, return true. If it is the same, we check if the characters are the same. We'll go to the next round of iteration. And then, if not, and still we can remove a word, we remove one of the ends and doing the recursion, right? So the maximum depth of this is only like 1. So it's okay, the recursion. And binary search tree iterator. Implement the iterator over binary tree. The iterator will be initialized with a root node. Connects will get next smallest number in the BST. Because it's a binary search tree, this one is the smallest. So next one is next smallest number will be 3, right? So actually, binary search tree means smaller on the left, right, middle on the right. So if you traverse through it, it should be in order traversal, right? Left, right. So if you do it in order traversal, yeah, we do the in order traversal, we will get the in order traversal representation in array, and we can just keep track of the index. If it connects, we just return that one, right? Yeah, cool. So that's it. In order traversal, binary search tree, add binary. I think we have done the add strings. This is a binary format. I think we just do the same. Don't mess up with the carry. Yeah, we set the maximum would be the same carry result fitted with 0, and we start if we sum them up carry and get update the carry and why we unshift 1? Huh? Ah, yeah. In the add strings, we initialize this length +1, right, with 0. But now here we could just check the carry. If there is a carry, we unshift 1. So yeah, it's basically the same. Lowest common ancestor of a binary tree. Well, for we given 2 nodes, we need to find the lowest common ancestor of a binary tree. So if we're going to search 5 and 1, it should be 3. If 5 and 4, it should be 5. Well, there are several approaches to this one. Like I've done it. Wow, it's like 4 approaches. First one is we return left node. We loop through it and search for P and Q, right? We traverse through all the tree, and if we found the target like left and right, we return that information to the parent. So this parent will return that also. So we walk, and this is what LCA left. Okay, with the common ancestor node, and we return another flag is left has P or left has Q, or has P or has Q for each node. So we walk to the left. If we found left, then it's left, and then we walk to the right. If it is left and right has it, and then we return it. And then for this node itself, for it, if the left has P, it has P. If right has P, it has P. And if the itself is P, then it has P. So we just return it. And this actually costs us linear time and space. So out of memory, we could also just keep track of the path, right? So we can do a search to collect all the paths to 4, all the paths to 5, and then we will pop the path out and find the first one, which is find the path which is first one is different, right? And then we return the result. If it's the same, yeah, that's the same node. But this actually out of memory, the time is also linear time, but space, it's not. It's very huge. Okay, so we improve the search first, rather than we return like this, a path, right? The path, we could improve it to for here. The path is empty. Oh no, here the path is actually an array. We return a new array, path contact. But actually, we could just use the same path, right? Yeah, if it is null, we return null. We push the node in it. If it is target, we return path. And if it is, we search with the path, right? And then F search, we return search. So this actually, we don't need to keep track of all the path for each node. We only track the path to it. But for this, we don't forget to pop the path, right? This is the path we need to search. This is what we need. So this actually will improve the space. And another way is global one path. Okay, so we use one path, just another variation of the path solution. But it's a little dirty here. I think the first one will be very easy to understand. Cool. Lowest common ancestor. This is the 5th problem. And the valid palindrome. Given a string, if it's a palindrome, consider only alpha numeric characters and ignore cases. Well, this is we could just check the index from left to right, right? If there are some characters we can ignore, we just move to the next one. So in a while loop, we check the head and the rare. If they match, we move next to meaningful characters, right? So you roll a 5. What I'm doing here. Okay, this is the regular. Sanitize it. Okay. This one. Wow, this is a brute force. We just split it, create an array, and reverse it, and rejoin it. Actually, it's this replace is still linear time, split linear time, reverse linear time, and the split actually create an intermediate array, which is not cool. Actually, we could use 2 pointers, like from left to from 0 and from the bottom, from the rear, and this will create O1 constant space and a linear 1 linear time. So this is not good, man. Vertical order traversal of a binary tree. We need to, so for a vertical tree, we need to return 9, 3, 15, 27. So this is a case that they have the same position. If the 2 nodes have the same position, then the value of the node that is reported first is the value that is smaller. So Actually, this is very simple. We do it at BFS with a queue. We do it layer by layer. But remember, if there is a node, okay, we loop through the whole children and find that if there's a left node inserted, which means if one of them is a minus the index, right? We keep a result. The array start adding is 0 for the next children. It might be -1. So we will loop through all the children, and if we find the index is smaller than 0, we check the left node inserted to true, right? And we keep track of the diff map. Why is this diff map? The index. I see. So we need to, rather than we insert the element into a result, we need to cache the diff first. Okay, we cache the diff and get the index, push it in, and then if there's left, there's right, we push them into queue, right? And we use a null as an identifier to do the while loop for each layer. And if left is inserted, we insert an empty array in the result. And before we doing it, we are asked that smaller value should be put first, but the order is not. We loop through the children from left to right, but it doesn't mean the left node here is bigger, is smaller than the next one. So we sort the diff first. We sort it and get the real index, and we push the real index in, right? And update the child nodes which are already in the queue. Yeah, the children will also be added, be updated with the index, because we push the index +1. This is the original index. When we insert it, all the index has changed. Cool. So actually, this is it. Not that difficult. It's only tricky about that is we cannot insert it beforehand. We insert it right away, but need to sort it and insert first. The order actually are kept from top to bottom, right? If we insert them and do the search, then the order will not be kept. So we need to first keep them layer by layer. Then in that same layer, it should be ascending order. That's why we keep a diff map sorted and then push them in. That's all for this one. Binary tree, vertical traversal. This is why these two are the same? We're the same. We need to return. Yeah, we need the same, but here's the same. Here's a different part. If two nodes are the same row and column, the order should be from left to right. So for this case, we don't need the extra diff cache. We just insert it, right? We can check the first node. If it is, oh no. We find if the left node is inserted, we insert the result, and we found it, and we just insert it because the order is from left to right. We don't need to cache it. We don't need to sort. So this is easier than the previous one. And this, I think this one should be hard. 2, 1, 1. This is how many? 3, 6, 9. A task until task scheduler. Okay. Add and search word. Well, design a data structure that supports following operators: add word, search word. So add a word bad, add a word dad, add a word mad, and we search pad, false. Search bad, true. Dot, add, true. B dot dot, true. Well, it's typical like a tree, right? We constructed for a node, we construct a node which has a character, and the next is a map of character. So for the word dictionary, we create a root, which is create a node, and use this as the start identifier. When we add a word, we first loop through the word, right, and get the layer to get do it layer by layer. For each character means a layer. So like for start, okay, see the character. If the root is not the root children, right? The root is empty. The children, if it doesn't have it, we'll insert it layer and go to set layer to the next one, and then we will check there until the traversal is done. So the tree must be appended, like APQ or APQL, APPL, Apple, we should need a set an identifier. Why? Because there might be APP and APPL, right? So we need to set an identifier. So for each layer, not only there will be alphabets, there will be a ending identifier, which is $. We set it $. So when we are doing search, we could just push, use BFS. We start from the first children, which is a start character. We loop through each word for each character in the search target. We get character, put an identifier to this round, and then loop through all the things in the queue, and we check it. If the character is a dot, then everything in the children could be possible, right? So for each of the head, okay. If it is not ending, we push the node next into the queue. And then if this the word, if the head has character, we push the head. This is a node, okay? This is actually array map string is to node. Okay, so for each item we push next character into a next node into the queue, and if the head has the queue, we just push that specific node into the queue. So if dot, like we were traversing to the L, if it is dot, we push all the nodes in. Okay, we must be super clear that the tree is actually a map, a node with a character, and the next is a map, node string, and next one is a map, and then not another bunch of characters. Those characters leading to another node. Cool. So we will add them. We set the layer. If the layer doesn't have character, we set it. Oh, okay. And the search. Okay. We set the root layer, the children of the root, to the queue, and then we search, right? We get each head, and if the character is dot, if it is dot, then the head is next. Yeah, here for each key node of the head should be pushed node next, and if not, we should put if the head has character. We push the head. Oh, this is confusing. Head characters next. Like APPL, we first get A, B, right? So we search A. Well, the A here, so we get the BP into our queue. So which means is the head is this. This is the head actually. Oh no, this is the head. This is the head. Okay, this head actually has the no. This is the head, and head next is this. So if head, we push the next and get the head. No. This is the head. I'm sorry. This is the head. Wait a minute. God. This is a confusing. The root actually, the next is the thing between this one. Actually, this like this, something like this. So what do we get? Actually, the knot here. So this is the first knot. We will check if it has the AB. If it has, we set to the next knot, right? The knot here. That's why we say if the knot has character, the knot has the character, and then we will set the head gets the character, which is this get character. The next is the knot. So we push the next in, and then finally if the queue is empty, we break, right? Yeah. If it's nothing, we break. Now, if the queue still has, if the queue, what? If the queue break, there are two possibilities that after we search, still we don't get the word, so it's default false. But if we stop, wait a minute. The I may be first be traversed, right? If we traversed, and Q is not break. Huh? No, wait a minute. If the all word is traversed, then the Q might be empty or might not be empty, right? If it is not, neither way, we can check if the Q, the rest Q, if it has dollar, is the ending identifier. If it is, we return true. So if we search apple, like APPAE, because we break when we, right here. Okay, so there's nothing to search, and that must be a fail. If we search for apple, and it should end at E, right? And E actually is a next not, and there is a dollar sign there. So there must be some so for a successful search, there must be something left in the queue with a not, with even it is only a not with the ending identifier. So we search on the queue, and if it is an dollar, then return true. If not, it's just false, right? It's false because it means it stopped earlier. There's no, yeah, the queue is empty, so it stopped earlier. Yeah, or the queue is there, but there's no word. Like we search apple, app. There is an apple, but there's no app. So we stop at apple here, but there's no identifier. So app is not in the word, though we have a tree, we have a path to app. Okay, so this is a little tricky. We need to pay attention. Add a search word. Okay, next one is 3, 6, 8, 9 task scheduler. Wow, this is huge. We're given an array representing task CPU, which contains the capital letters, where different letters represent task. Okay, we need to keep it. There's a non-negative cooling interval. That means between two same tasks, there must be at least n intervals. Well, suppose something like this, A, B, B, B. We actually need to find, we need to find the biggest one, right? The longest the task with the most count, and then insert the rest tasks into them, right? So we found like A and then BB. So we put A and put the task into the space. Put the space periodically, like looping through, right? So we count each task, and it gets the maximum count. Count it, gets the maximum count. Okay, so determine how many tasks got to the max count. Task count of max count. If count equals max count, which is the A or B, then we task count must be plus with 1. Okay, so suppose there's A, and then B, right? B. If that's the case, we need to A, and then B. For not, if they are smaller than them, we can safely put them all into these 3 spaces. So the interval requires actually will be task count of max plus the rest, right? Max count This is the space, right? This is max count, yes, 4. So now we get 3 slots times n minus 1. N is a cooling, so this one, which is n. So there must be at least 2 intervals, 2a, b, b, a. So this one plus this one, right? So the idea is, keep it simple. We find the maximum count. Actually, will be a here, or if b is the same, we need to put b. So the count here and here are the same. This, which is n minus n plus 1, except the last two, right? These two only occurs when there is more than one max, at least one, but there might be 2. So that would be the count of max count. So we plus these 2, and then we just count directly with this. Cool. So this is max intervals required. This is what we need. Of course, if it is more than that, then we just the holes will all be filled, right? So we just compare it with task length and the interval required. Cool. This graph is very important. Let's just review it one more time. It's very important. So we need to find the maximum, right? A, and then the space could be used to insert the rest tasks. But if the task is at least equal to it, equal larger, or they won't be larger because largest is A, it might be equal. So if it is equal, like B, we put B here. So the count would be the place here plus the area, the slots here, right? This is what it is needed to. This will simple. This is n plus 1 times here, which is the max count minus 1. Max count is 4, so here is 3 times n minus 1, and plus these two. These two could be to do counting. Well, linear is constant. Cool. Task scheduler. Okay, in the next video, I'm going to take the next 10 take a look at the next 10 problems. Hope this video helps. See you next time. Bye bye.